let's talk a little bit about the conservation of angular momentum. And this is going to be really useful because it explains diverse phenomena in the universe, from why an ice skater's angular speed goes up when they tuck their arms or their legs in, all the way to when you have something orbiting around a star, and the closer and closer it spirals in, it seems like its rotational velocity, its angular speed, is picking up, and it starts to rotate faster and faster around the body. You'll see that if you see simulations of astronomical phenomena. So the big picture here is if we have our initial angular momentum for a system, and we'll think about that in a little bit, no matter, as long as the system has no external torque applied to it, then your final angular momentum is going to be the exact same thing. And so one way to think about it, let's imagine that I have some type of spinning thing over here. I have some type of mass. Let's say it's on a table I'm looking from above, and a point on the outside of this disk is spinning in this direction with a velocity of magnitude v. And let's say that there's a clump of clay, of orange, maybe it's Play-Doh or clay or something, and it has a velocity going in this direction. It's on a collision course with this object, and let's say it has a velocity of 5v. And so if we think about this disk clay clump system, and so you always have to specify what system you are talking about. So if you think about this entire system, how does the angular momentum change before these two things collide and then after these two things collide? So actually, let me draw the after the collision scenario. So the after the collision scenario, it looks something like this, where the clay has now clumped on to this, and now they are going to be rotating together. And I haven't even told you the mass of this disk or the mass of this clay, so it would be unclear in which direction they would now be rotating. But how is the angular momentum going to change from this state, from the initial state, to the final state? Pause this video and try to think about it. Well, you might have guessed. Since we said, look, we have this whole system, and we're not applying any external torque to the system, our angular momentum is going to stay exactly the same. Now, we have to be careful. If I told you the system was just this disk, not the clay clump that's on a collision course with it, then the angular momentum for the disk would change. But why is that? Does that defy the conservation of angular momentum? No, because this clay clump, when it collides, would be providing an external torque to the system if we define the system to just be the disk. But since it's the disk plus the clay clump, and we have no external torque to that combined system, then our angular momentum is not going to change.